Hello, my name is Ananya Kapoor, and I'm a graduate student at the Konova Addiction and Decision Neuroscience Lab at Rutgers University. Today, I will be presenting our work on investigating the role of dopamine in patch foraging behavior. A common characteristic of addiction is consistently pursuing a course of action despite diminishing returns. This is most directly observed in drug-seeking behavior and drug use, despite reduced benefits derived from the drug. Using decision neuroscience, we tested a computational framework to explain this maladaptive behavior, centered to foraging. Oftentimes, decisions are not made between two independent options, but rather in a sequential manner, where consequences of the first decision affect the following decisions. Patch foraging is an ideal framework to observe serial decision-making because of its ecological validity, inspired from the way that animals make decisions to maximize fitness. The subject's goal in this task is to navigate a patch-abundant environment to maximize the total reward collected in a fixed amount of time. Subjects have two choice policies, either harvesting from a current patch, known as exploiting, or leaving the current patch to explore other potentially richer patches. Therefore, subjects need to decide when they should exploit the current patch or explore other patches in the environment. We can characterize the optimal patch leaving time through the marginal value theorem. This analytical solution tells us at which average reward value the potential earnings from the rest of the environment equal the immediate rewards from the current patch. Indeed, leaving the current patch at this optimal reward value for every patch in the environment will maximize the total reward earned. We will formalize this reward value at exiting the current patch as the exit threshold. This is the reward value a forager collects at the trial decision immediately prior to exiting. This exit threshold value is a subject's estimate of when the immediate rewards from the current patch equal the average environment reward. Hence, a good forager will exit at reward values that are close to the optimal exit threshold as given by the marginal value theorem, abbreviated here as MVT. Therefore, large deviations from the MVT optimal value, either leaving too late, known as overharvesting, or leaving too early, known as underharvesting, will lead to suboptimal total earnings. Indeed, comparing each subject's exit threshold to the optimal MVT value forms a consistent decision pool. Theoretical foraging models and animal work in foraging suggest a role of dopamine in overharvesting behavior. Tonic dopamine is hypothesized to be involved in patch leaving behavior because when levels of tonic dopamine are low, average environment reward will be perceived as lower, leading to overharvesting. The relationship between overharvesting and dopamine is relevant to addiction, given that chronic drug use is known to lower tonic dopamine levels, indicating that addiction may be marked by overharvesting behavior. To investigate how individuals with opioid use disorder, also known as OUD, perform sequential decision-making, we designed a patch foraging task and recruited 42 patients and 33 controls. In the task, subjects see a tree from which they can harvest apples, which are worth real money that are earned at the end of the task. They either choose to harvest a tree to receive rewards or travel to a new tree while incurring a travel time delay. And with each harvest, the supply of apples in a given tree are depleted, reducing exponentially the total earnings from the current patch. This framework is defined by multiple parameters, including the initial patch richness, reward depletion rate, and the time delay when traveling from patch to patch. Our task manipulates travel time in a counterbalanced design while keeping both patch richness and depletion rate constant. Given that we know that the substantia nigra ventral tegmental area complex, also known as the SNVTA complex, is the principal site of dopamine production, we sought to image these areas to determine whether differences in foraging could be explained by the long-term function of the dopaminergic system. We can image the system using neuromelanin-sensitive MRI. Neuromelanin is a dark pigment synthesized via the iron-dependent oxidation of catecholamines such as dopamine. Neuromelanin gradually accumulates over the lifespan in organelles in the cell bodies of dopamine-producing neurons in the SNVTA complex. This structural scan makes neuromelanin-containing nuclei hyperintense, allowing us to measure the concentration of accumulated neuromelanin. Neuromelanin concentration can be used as a proxy measure of the long-term function and production of dopamine in the SNVTA complex. On the left, we see exit threshold behavior of two representative subjects with respect to the MVT optimal values. We see that the control subject is generally aligned with the MVT optimal for both short and long blocks, while the OUD subject consistently overharvests. A linear mixed effects analysis predicting exit threshold yielded a significant travel time and diagnosis effect, indicating both that subjects adapt their decision-making strategy to changes in travel time and that patients consistently have lower exit thresholds than controls. Another way of analyzing task behavior is by looking at the distance from the MVT optimal value, known as the sign deviation from MVT. A sign deviation that is less than 0 indicates overharvesting, and a value greater than 0 indicates underharvesting. A linear mixed effects model predicting sign deviation from MVT yielded a significant diagnosis effect, indicating that OUD subjects consistently overharvest with respect to the MVT optimal value. We then sought to relate increased lifetime opioid use with exit threshold and found that increased lifetime use is significantly associated with lower exit thresholds. Indeed, these results suggest that increased lifetime opioid use could cause misperceptions of the average environment reward value, thus resulting in overharvesting behavior. Prior work has proposed that dopaminergic activity in the VTA is involved in this type of effortful decision-making through its connections to the anterior cingulate cortex and nucleus accumbens. Hence, we sought to determine a neuromodulatory basis for overharvesting by relating neuromelanin signal in the VTA to exit threshold. A linear mixed effects analysis on 25 OUD in 28 control subjects showed that mean VTA neuromelanin signal reliably tracked both exit threshold and sign deviation from MVT, suggesting that tonic dopamine in the VTA, as proxied by neuromelanin signal, reliably tracks the subject's perception of the average environment reward. Moreover, a separate analysis in patients alone showed a significant relationship between neuromelanin signal in the VTA and exit threshold, indicating that the mechanism of reward tracking does not differ between patients and controls. These results were also confirmed in a voxelwise analysis of the SNVTA, where we found that the majority of the VTA voxels were significantly associated with mean exit threshold. Indeed, this analysis shows that the VTA selectively tracks mean exit threshold as opposed to other dopaminergic rich regions, such as the substantia nigra pars compacta or the substantia nigra pars reticulata. Our work investigates how a proxy measure of tonic dopamine, that is neuromelanin, affects serial decision-making in a patch foraging task. We found that both controls and patients generally overharvest with respect to the MVT optimal value, and that patients overharvest significantly more than controls. To explain this overharvesting behavior in patients, we found that a significant association between increases in lifetime opioid use and lower exit thresholds exist, suggesting that maladaptive reward tracking could be impaired by increased opioid use. Guided by the literature on tonic dopamine and reward tracking, we found in our data that decreased neuromelanin signal was associated with lower mean exit threshold. Indeed, this relationship was also present in our opioid-using participants, suggesting that reductions in VTA neuromelanin signal from chronic drug use could cause overharvesting behavior. Future directions with this work include drawing a direct parallel between real-life decision-making and addiction, as well as explaining additional cognitive drivers of foraging decisions, such as risk and delay discounting. I would like to give a special thank you to my co-authors, patient and control participants, funders, and to you for listening. Thank you.